Okay. Uh,
Okay. So, hello everyone. You've already seen kind of contents of the lectures, and you can see that it's not everything about polarization. One is saying very little about the source of the polarized radiation or what happens to it in transit. It's really more about tools to describe polarization. And I should say why I found this area interesting. I mean, not just now, but over the years, is that there are so many different ways of looking at the same thing. And it also has interesting connections with quantum theory, with mathematics, and somewhat to my surprise, even 20th century mathematics. We normally use the same mathematics that Newton used, and we'll see this as we go along. Okay. So with that kind of brief introduction, let me begin by sharing. Okay. So I hope you can all see this blank slide, which simply says polarization 1. And
no, we think which is Newton on polarization here.
oh, okay, fair enough. So, end video. Okay, and let me hide the floating console. Okay. So, when we think of the discovery of polarization, you think of this thing which is there in all the textbooks, or at least the ones that I used to read, that some sailors went to Iceland and they complained about seeing double, which is not infrequent with sailors who have to keep warm in a cold climate. But one Danish gentleman took them seriously and studied the propagation of light in calcite and found that indeed it split into two, double refraction. And then the legend, which is true, but not the whole truth.
Sorry, excuse me, Rajaram. I think we are not seeing the right slide. We are still seeing Newton on polarization.
But that is the one, actually.
Okay, perfect. Sorry about that.
That is the one, yeah. Except that it doesn't seem to be moving. Let me see. Should move. There we are. Okay. So the part of the story which is not told, we are all told about Huygens, who, of course, gave this brilliant theory of double refraction. It's a geometrical theory, saying that the wave doesn't have to be just spherical, it can also be spheroidal. But he, as far as I can judge by reading his treatise on light, didn't say anything about polarization or any property of light, actually. He just said, I can explain the direction in which these rays go by this construction. He also, interestingly, has no mention of the wavelength. Now, I'm contrasting this with Newton, who had the book on optics, and he's made the villain of the piece because he believed in a particle theory of light. But nevertheless, he actually has a number for the wavelength because, after all, he saw Newton's rings. And he has this remark in the end of his book. So he seems to be the first person who has said, I mean, you have to interpret this, I don't know, 18th century English, early 18th century English, two opposite sides, right? Whatever that is. But two other opposite sides. So one of the points I'd like to make, maybe redundant for the audience I've seen so far, is that you should think of linear polarization as a double-headed arrow, right? It's true that the electric field at any moment is pointing in one direction, but femtoseconds later, in the case of light, it's pointing in the other direction. So this is just a brief digression on the fact that Newton had his take on polarization. So the standard history is that Huygens explained double refraction at geometric sense, but the idea that you had a transverse wave It was still not electromagnetic by 1801 when Malus, okay, my pronunciations of many of these names will not be the standard ones, gave us this law that you had some amplitude, and if it made some angle with some axis, then the intensity you saw was the square of that cosine, right? So that is linear polarization. And then once people started, measuring polarization and subjecting every known substance to these experiments, it wasn't long before the concept of circular polarization came in, right? And this came from the rotation of linear polarization. So again, the history is that it was first found in the mineral quartz by Arago. But as astronomers, we can be proud that Herschel is the one who said, picking out crystals of quartz which are mirror images, found that it rotated in the opposite direction. Okay. And then, of course, in solutions, and of course, Pasteur, whom we know for inventing vaccines, but he did this completely brilliant exercise of showing that tartaric acid from a biological source has one-handedness, but if you just make it in the lab, it's a mixture. And closer to radio astronomy, and I find this experiment also quite incredible. Why would Faraday take, a piece of glass, wind a magnet around it, and send polarized light through it? I have absolutely no idea. But he discovered that you get a rotation, right? And of course, that has been well exploited in radio astronomy. So let me touch on circularly polarized light. And immediately you run into this problem of convention. So the convention, which I hope I will follow consistently. So you're now supposed to be looking at the source. And the electric vector is shown in the transverse plane. So Z is pointing to you, and you have X and Y. And if X to Y is the conventional positive sense, so this is right circular. Okay. Now, just to make life more interesting, this is as a function of time at a given place. If you, on the other hand, froze the time and saw how this electric field behaved as a function of position along the direction of propagation, you would get a left-handed helix. Okay, so let's just stick to the time variation. And of course, as radio astronomers, you should also know that if something bounces off the dish and comes to your feed, then it also flips its sense of circular polarization. I mean, it rotates in the same direction, but the direction of propagation has changed. So, this also illustrates the point, which is responsible for the work on the rotation of polarization that I told you about, that you can think of linear polarization as made up of superposing right circular and left circular. And this now depends on the relative phase, when the two vectors sort of cross each other. So the way I have set it up, they cross along the x-axis. And the y components, if you have equal amplitudes, they cancel. And we will see what happens when they don't have unequal amplitudes later. So we will have circular polarization and we will have elliptic polarization, but we will only have linear algebra. Okay. So let's start with this simple setup where you have crossed. Crossed means at 90 degrees to each other in the xy plane. And you have a single frequency. And this is going to be the assumption for the rest of today's talk, which really means that the entire talk is fiction. Okay. However, this fiction will help us when we actually have to face facts. All right. Now, the reason why it's a fiction, of course, is that this model of having precisely one frequency along X and the same frequency along Y, possibly with a different magnitude and a different phase, this model can never explain unpolarized light, as we will see. But let's not worry about that for a moment. Okay. So the algebra is, the electric field is real. Okay. So it has an amplitude and it has a phase. And I think this is a phase retardation. if it's put this way. Okay. Now, again, there is a bifurcation of conventions, but I think physics and astronomy literature, when you make this complex and take the real part, right, the time is given a minus sign. So then this phase gets a plus sign. So e raised to I phi is phase retardation. That's a good thing to keep in mind. Okay. So this is for the x component of the electric field. And no surprise, the y component has a very similar expression with its own amplitude and its own phase. But we'll find it very convenient to keep working with these two complex numbers, but keep in mind that you will have to take the real part if you want to really deal with the electric field. Okay. Now, the first thing one can do with this pair of equations, which you'll be happy to know I'm not going to do, is to expand out the cos. We'll have cos and sine. And then you can solve simultaneous equations for cos and sine, which will be in terms of Ex, Ey, A1, A2, phi1, phi2, etc. And then you can use cos square plus sine square equal to 1. So that's the kind of painful way of seeing that the path taken in the Ex, Ey plane is an ellipse. So we'll find a less painful way later on, which is why I'm not doing this. So the first thing we can do, since everything has the time dependence of exponential minus I omega t, is to suppress this. Okay. And the two complex amplitudes are packed into a complex column vector in 2 dimensions, a 2 cross 1 matrix. Right. So I hope I've been consistent in using some kind of italic boldface for these matrices. And this is just a definition, right? I mean, just calling these two numbers Z1 and Z2, the two complex amplitudes of the X and Y polarization. Now, the moment you give a mathematician two-dimensional complex vector space, he will want to do a few things. He would want to add them, which you can do. And this is the case, an example of coherent superposition. Of course, everything is coherent. I mean, in this kind of setup, single frequency setup, the relative phase of two things cannot change. Okay. You can also take this and multiply it by overall by a complex number. Overall means same complex number multiplies both Z1 and Z2. In that case, what happens is the magnitude of the complex number blows up or attenuates the strength of the wave, but in the same way for both the components. And the phase of that complex number is again a common phase added to both of these. So it simply means that you're looking at the thing at a later time. Okay. So this operation of just taking, our vector, which represents polarized light, and multiplying by some constant is essentially changing the scale and changing the phase on this elliptical orbit. Okay. Now, the other thing you can do, and which we will do immediately, is to change the basis. Now, the simplest change in basis is to change the basis, go to some other x and some other y inclined at some angle in the same xy plane. And that's very straightforward. But one can do more. And in fact, in every radio telescope or many radio telescopes, this is what happens, right? You can also break up things into left circular and right circular. So let's see how that works. You have a complex amplitude multiplying 1, 0. So it's just the same Z1, Z2 rewritten as in terms of a basis. So 1, 0 is, some unit electric field polarized along X, this one along Y, and these are the complex coefficients. Now, if you wanted to describe a right circular light, you would want the Y component to lag the X component by 90 degrees, right? So hence the 1i. And you might want for the total intensity, total power to be the same. that is the sum of these squares, absolute squares, since we are dealing with complex numbers. So you could stick in a 1 by root 2 to ensure that. And of course, the left circular is this. So the same thing which is represented in the linear basis by Z1, Z2 is represented in the circular basis by ZR, ZL. And now it's a simple matter to just read off what Z1 and Z2 are going to be, just the coefficient of the upper line and the lower line, and write it in a matrix form. Okay. So this doesn't require much comment. But you might want to do the opposite. You might want to express the amplitudes and phases of these right and left circular descriptions of the same wave in terms of the same amplitudes which were along x and y. Okay. So you have to invert this matrix, which is easy to do because it's a unitary matrix. So you just have to transpose it and take the complex conjugate, which is what I did. And I also checked by multiplying that indeed the product is 1. I mean, so a change of basis in general is given by this kind of transformation. And this particular basis is, of course, quite important in radio astronomy. Many radio telescopes have circular. I think GMRT has a mix. And I think, if I'm not mistaken, VLA was circular. I don't know what it is now. The Australians said, no, we will go linear. Westerbork went linear. And in fact, so there's many, many reasons why people make these choices. I wouldn't go into them, but there are good reasons. Okay. So that's a little bit of algebra. Now let's think of the thing more geometrically. Okay. So the way that people thought about it, even before electric fields, before Maxwell, was that you had ether and you had these transverse vibrations, and some particle executed some path. Okay. So today we would say electric field. And the most general case is an ellipse, but it could also be traversed clockwise or counterclockwise, right? So the same convention that applied to circular polarization is also applied to this. And now what we're going to do is we have 2 complex numbers, so 4 parameters, right? But we're saying we're interested in classifying, mapping out all the possible states of polarization, whereby state, one means we can standardize the size by making the power 1, for example, which is what we did with circular. And we can also say the phase would be a dot on this ellipse, right? Telling you where it is at a given time. But maybe you're not interested in that. So then you end up with 2 parameters, right? One would think, right? So state means ignore the intensity and ignore the phase, okay? So let's look at all possible states of polarization. And basically, you are only worried about the B by A ratio because you're worried about the shape, right? So that's one parameter. And the other parameter is the orientation of the major axis with respect to, let us say, the x-axis. Okay. So we're calling this angle alpha. And do bear in mind that alpha only goes from 0 to pi. Because by the time you reach pi 180 degrees, the major axis has returned to its original configuration. Now, if you had put a dot on this orbit, then, of course, the phase would have changed. But we are saying we're ignoring the phase, right? So this alpha goes from 0 to pi. And then the B by A ratio, well, B ranges from minus A to plus A. The minus requires a bit of explanation. It's just a convention that if you make B negative, it's as if the sense of rotation has changed, right? Now, so this would, B by A really goes from -1 to +1. And for reasons which will become apparent a little bit later, you define something called beta, which is the arctan of B by A. Okay. So it only goes from -45 degrees to +45 degrees, right? Minus pi by 4 to plus pi. But the sign gives you the sense of elliptic polarization. Okay. Now, of course, you can continuously increase B, but the moment it crosses 1, then you say that alpha has just jumped, right, by 90 degrees. Now, it's kind of interesting that you have these angles, which one goes from 0 to pi, and the other goes from minus pi by 4 to plus pi by 4. So, I mean, in a somewhat ad hoc way, you could double them. Okay. Right. So then you'd get an angle going from 0 to 2 pi, and you would get another angle going from minus pi by 2 to plus pi by 2, which are just like the longitude and latitude on a sphere. Now, of course, that doesn't make it a sphere, but we will see that this is actually a very nice way of representing polarization. Right. So I hope this is clear. So let's say alpha is 0 is here, and then alpha is gradually increasing, and comes pi by 2 and goes to pi. And that's the end. Okay. Right. And the same applies to any elliptic polarization also. This also has an alpha of 0, this has an alpha of pi by 2, and this has an alpha of pi. And 0 and pi are really the same. So at the moment, we really have a cylinder, right? If you thought of this as a map, you can certainly glue this left-hand side to this right-hand side. But it's also true that the moment you reach b by a of 1, alpha ceases to, alpha ceases to have meaning, right? There's no major axis. So it's a bit like on the Earth, when you reach the North Pole, your longitude has no meaning. So really, the fact that these elliptic polarizations become circular polarizations tells you that the sphere is the right way of thinking about the totality of all states of polarization. Okay. Now, of course, the coordinate alpha was fairly natural. The coordinate beta was a little ad hoc, but we'll come back to that later. Okay. So this is the picture of Poincare, who actually has a very interesting relationship with physics. He was considered a giant in the mathematics of the 19th century. I mean, he virtually invented topology, right? Except he called it by a Latin name, known for his depth. Interestingly, he was trained as a mining engineer, so maybe that's why. And you'll find that many of these French people actually went through these great schools which are set up by Napoleon to train his engineers. But anyway, and this is just a side remark, but he actually decided to lecture on optics for 2 semesters. And I tried very hard to get hold of those lectures. The best I could do was in Bhaskaracharya Pratishthan of Pune. I found a German translation of those lectures. But anyway, so it's hardly a page where he does. But he didn't. I mean, you don't expect a great mathematician to, do ad hoc things like what we've done. So he had a much deeper way of doing it, and we will look at that now. Right? So for that, let's digress into something which is called stereographic projection, and Poincare did not invent it. In fact, it's very much there in the work of Ptolemy, who wanted to represent the sphere on a plane for obvious astronomical reasons. And the way that's done, and people suspect that he borrowed this from earlier people like Hipparchus and so on. So here's the sphere. Here is the theta equal to 0 arc on the sphere, which is parallel to the x-axis on the plane. The sphere has a diameter of 1. And there's a mapping from any point on the sphere, theta phi. So right now I've shown a point which is kind of behind. So the dotted line is inside the sphere, and then it continues, and it hits the plane at a point x plus I. Now, the geometry of this triangle, right angle triangle, from here to this point, tells you that this angle is half theta, and therefore the point theta phi maps to cotangent of half theta into exponential of I phi. Okay. The phi angle on the sphere is the same as the phi angle on the plane, as you would guess. Okay. Now, this just tells you how to send one complex number, get one complex number from a point on the sphere, okay? Or map one complex number back to the sphere. Now, we started with two complex numbers, okay? However, for our immediate goal of classifying the states of polarization, one has this notion of equivalence, right? If you have these pairs of complex numbers sitting as a vector and you multiply both of them by the same number, that's really the same state of polarization. They only differ in magnitude and phase. So really, it's only the ratio. And that is one complex number. So that's how you... So the ratio of the two complex numbers will encode the relative amplitude and the phase difference, which is what you need to plot out the orbit. Okay, so now I have just written down two numbers whose ratio is cot half theta and exponential I phi. Okay. Now this could be in any basis, but for now I'm choosing the circular basis. Okay. So we have left here and we have right here. This simply is a definition. So ZL is just shorthand for this, and ZR is just shorthand for this. The next one is in equivalence. So one has decided to divide both these by ZR, the ratio that I was talking about. And here you have Z, which is ZL by ZR, and you have just one here. Okay. Now, so that's how a single complex number can represent a state of polarization. Okay. There's just one point which has to be allowed for. What happens when ZR is 0? Okay. Which means this polar angle theta is 0, which means you're sitting right on top. And that's the one place where, if you continuously move this point to theta equal to 0, this line would become horizontal and would never touch complex plane. Okay. And not only that, it appears that a single point on the sphere is now representing a whole circle of points at infinity. If you believe there are points at infinity on the complex plane, then all those points have different phases. They have some infinite magnitude, but they're all being mapped to the same point. But that's actually not a defect. It's needed. Because if you think about it, if ZR becomes 0, the phase of ZL is irrelevant. Okay. Or in this representation, you could say, if Z goes to infinity, it's infinitely bigger than this 1. And therefore, the phase of the Z is unimportant. So this particular mapping of the complex plane takes infinity to the single point. Now, Poincare did not invent this. It was invented by Riemann in order to deal with situations where functions become infinite. He found it convenient to put them on a sphere. Okay. So let's just remember this because we're going to use it. Okay. The left circular has an amplitude of cos half theta, and the right circular has an amplitude of sine half theta. And here, the left circular actually lags behind the right circular by phi. So, so I'm now going to add this left circular and right circular, which have different magnitudes. So let's see, this one is right, no, this one is left circular, right? Going this way. And this is right circular going in the positive sense. And we are in the upper hemisphere, right? So that means sine theta by 2 is less than cos theta by 2, okay? Now, I've got it at, say, t equal to 0. Let's say right circular is here, but the left circular lags behind by phi, okay? So if you wait a little longer, the two will cross at phi by 2. So already you can see that that angle phi which appeared gives the major axis, right, of the ellipse. First of all, it's very clear this is going to be an ellipse because on the when you project both these along the bisector, both of them look like cos omega t. They both are, I mean, this component has the same phase. And of course, if you look at the perpendicular component, since this is bigger, it will dominate, right? So that's how I got this B by A ratio of cos half theta minus sine half theta in the numerator and the sum of the two in the denominator, okay? So we now have the orientation of coded into the angle phi on the sphere, right? Except that it's really phi by 2, okay? So the angle, the polar angle on the sphere, the phi angle, is actually double of the angle made by the major axis with the x-axis, which is exactly what we did, right? Now, this is certainly at least I find it a nicer way of saying that it's an ellipse, but nothing comes without some pain. So you can exercise your trigonometrical skills to show that this expression is the same as the tangent of half the latitude, okay, pi by 2 minus theta. So this stereographic projection kind of justifies the ad hoc choices that one has made. And it also tells you a couple of interesting things, which we'll see. Okay, so let's go back to algebra now. Okay. Now, you might want to look at what the optics people call the intensity. And I guess you would call it flux or power. And well, at a basic level, it is E cross H, right? And it's E dot E. I guess since E is perpendicular to H. I mean, with a proportionality factor, which depends on the units. And since if we deal with the original real form, we'd have an A1 square cos square, right? Whose average is, cos square average is half over a whole cycle. We don't have to average over more than a cycle because it just repeats, right? We are in this fictitious monochromatic universe. So A1 square plus A2 square. And now we can use the complex form, right? A1 square is EX star EX, and A2 square is EY star EY. And it can also be written in a matrix form. So you have EX star and EY star made into a row vector, and EX and EY made into a column vector. And you multiply the two, it's 1 cross 2 multiplying 2 cross 1. So you get 1 cross 1, which is a number. In this case, a positive number, in fact, sum of two squares, right? But in matrix notation, it would be written as this vector E and E dagger. This is the best I could do for dagger and LibreOffice. Okay. So E dagger E is our formula for intensity. Okay. So promised you something to do with interference. So now let's imagine that we are superposing an EA and an EB. Okay. Right. So what one has to do, right? And these could be two completely different polarizations, but completely coherent, mind you. So you have the two pieces. So you just multiply it out, right? EB and the dagger of the same, and you will get 4 terms. Okay, so just plugging EA plus EB into this expression. Now the first 2 terms are just the intensity of the A beam and the intensity of the B beam. Okay, that's not interference, right? So all the interference is contained in these 2 terms. And of course, they're complex conjugates of each other because the intensity is real for sure. Okay, so EA dagger EB, conventionally, we call it the interference term. Okay, keeping in mind that the actual interference term is the real part of that. Okay. Right. Now, again, if you had this mathematician who wasn't interested in radio astronomy or polarization at all, but you just gave him a 2-dimensional complex vector space, one of the first things that he or she would construct is this quantity, EA dagger EB, and it is the analog of a dot product And remember, this is complex, right? But one should also say that the imaginary part is experimentally accessible. For example, if A and EB were being interfered in a Young's experiment, you could move along the screen and you could change the relative phase. So if you change the relative phase by 90 degrees, you would now be dealing with right? One of them would acquire an extra I, right? And of course, the dagger would acquire a minus I. So that way you would access the imaginary part. So you should think of this as a complex number whose real part would give you the interference term, but the imaginary part can also be measured by just shifting the phase of one of the beams. So the situation where you do not get any fluctuations in intensity as you move along this Young's experiment screen, which was the classic early 19th century test of interference, right? Once Young had done the job, his contemporaries in France would interfere these two slits. They would put all kinds of crystals and so on in front of the two slits, okay? And look for situations in which the fringes disappeared, okay? And if the fringes disappeared, it really means that both the real and imaginary part of this A dagger EB or inner product or dot product are zero. So, so there are the Fresnel-Arago laws. And so in the case of two perpendicular linearly polarized waves, it's particularly obvious because the dot product of I with J is zero, right? So you don't have to worry about the interference term. Not so obvious for opposite circular waves, but one can actually check by plugging this in. We already have a formula for EA for right circular and EB for left circular. One will find that's again zero. So the general concept is that such states are called orthogonal. Now, the most general case of orthogonal states is two ellipses, same axial ratio, perpendicular major axis, and opposite senses of traversal. Now, so instead of checking individual cases, if we check this most general case, that would take care of the linearly polarized case and the opposite circular and so on. Right? So, and the claim is that on this Poincare sphere, which I've returned to, these are actually antipodal points. Okay. So here is what we saw earlier, the point living at theta and phi on the Poincare sphere. And we also know how to convert theta and phi to our alpha and beta if you want. Right? Phi is 2 beta, and this is awkward. It's an angle measured from the pole, but you have to convert it to an angle measured from the equator. Okay. But never mind, let's just stick to this. So this is EA. Now the antipodal point is obtained by changing theta to pi minus theta, right? So that you flip your hemisphere, but also increasing this phi by 180 degrees. Okay. So that accounts for this minus sign, right? Increasing phi by 180 degrees. And to think about it a little bit, sine of half theta and cos of half theta interchange. If you replace theta by theta, pi minus theta. So this is the orthogonal. Well, I haven't said it's orthogonal, but this is the antipodal state. And now it's a straightforward view. Just a small precaution is you have to take the dagger of this. Okay. And when you take the dagger of this flip sign, and therefore when it multiplies this exponential I phi, you just get cos into sine, minus sine, and you get sine into cos. So this is the most general case of orthogonal polarizations. Orthogonal in the sense that the interference term vanishes. Okay. It's easily verified, and we've just done that. This is here. I now come to something which I would really deal with in more detail in the last talk. But since we've set up all this machinery, it's worth talking about it now. Okay. So we already talked of multiplying both components of the vector by the same complex number, little g. So little g is just a complex number. Okay. And we know what that means. Now, if you weren't worrying about polarization and you're only looking at let us say, the X polarization on all the antennas, right? You might still worry because you're trying to measure visibility, whether in your system there is some G sitting there for each antenna, and which could be different for different antennas. Of course, the same for all the antennas, the situation is slightly better, but in principle, it could be different for different antennas. Now, this is what the optics people would call an aberration. It's a deviation from the ideal behavior of your system, but nothing is really ideal, right? So at some level, any feed would have, if you want to compare what you actually measure to what actually came into the telescope, they could be related by small g, even in the case of a single polarization. Okay. Of course, the magnitude might be 1, the phase might be small. I mean, otherwise our engineers would be very offended, but it's there. However, when you come to polarization, it becomes richer. Okay. You have a 2 into 2 matrix capital G, and think of it as acting on the left on this column vector, which has 2 numbers. So what are you doing? You're mixing them up, right? So the output of this is, let us say, what you measure. The input is what comes from the sky. And again, no system is perfect, right? It could be that the 2 diagonal elements are very close to 1. It could be true that the 2 off-diagonal elements are very close to 0. They need not be the same, by the way, right? They could be different, okay? So this is what the concept of this aberration or gain becomes if you're dealing with a fully polarized case. It's multiplied by a general 2 into 2 matrix, okay? Acting on the individual. And I emphasize that this is a non-ideal measurement. And of course, radio astronomers have known this for years, right? And conventionally, one still thinks of complex gains for each polarization and leakage terms. So it's D terms. So I'm sure many of the experienced people in the audience would be determining the D terms when they do their mapping, okay? And one way, of course, to determine them is to calibrate. Of course, that means you trust some known source, maybe a polarized source as well, okay? And how exactly to do this is quite a long story. And for those who are interested, I will I was hoping to put up some resources. But of course, if it's the kind of expert audience I saw at the beginning of the talk, then the resources might be redundant. There's a famous paper by Hamaker, Brigman, and Salt from Westerbork, where they go into the nitty-gritty of how to get all these things by observations of sources. Okay. We will have something to say on this, but downstream. Okay. So I guess what I would like to leave you with, right, is this kind of parallel. I find it intriguing that, right, you take a person who just does linear algebra and everything they do seems to have some meaning in our context. So you have an incoming electric field, which is just a complex column vector. The power of flux is actually the norm. I earlier talked of an inner product or a dot product. So norm is the dot product of something with itself. Okay. And remember, this is the complex dot product, EA dagger, EB. Okay. Now, what is the feed? The feed is something which takes the incoming polarized radiation and gives one output. So I'm not talking about dual polarized feed. So if you're talking about dual polarized feed, I'll look at just one of the wires coming out. Okay. So it gives you some combination of these two. Okay. So if you had Z1 and Z2, it just gives you some A times Z1 plus B times Z2. And if you write that in a matrix form, right, you can put the A and B into a row vector and multiply it by the Z1, Z2 as a column vector. Now, mathematicians like this concept that the row vectors are objects which, when they act on a column vector, give you a scalar, 1 cross 1. So it's called the dual space, if you like that. But in any case, that's what a feed is, a single element feed. And the response of feed to the field is this inner product, right? Row times column. Now, we looked at the case of converting linear to circular, which happens in many radio telescopes. And I think there are different devices, but there's something called a quadrature hybrid, which is, I believe, designed to give you A plus IB and A minus IB with equal amplitudes. And this, in mathematical terms, is a change to a basis, a particular change of basis. Okay. Now, in this case, we would like the power in these two to add up to the incoming power. So let's say it's a lossless device. And to a mathematician, this is a unitary transformation. And finally, we saw this lossy, leaky device, which does arbitrary linear combinations to the two incoming fields. And that's a general linear transformation. The one thing that we have not seen so far is what is called the outer product. So you have let's see, 2 rows, 1 column, right? 2 cross 1 column vector. And then if you multiply it by a 1 cross 2 coming on the right, that's called the outer product, because that will give you 2 cross 2. It will give you a matrix, right? Now, what is that? Well, we have to keep something for the remaining lectures, right? So watch this space. Okay. Finally, I want to tie up. I've shown you this algebraic way of looking at things you can do to polarization. Turns out that the Poincare sphere can also do this. Okay, can do many of these things. The first thing is it actually gets the topology of the polarization right? I mean, that's the discussion we had when we said that as you move along these lines of longitude on this, and you merge, then all the ellipses become the same, right? So basically, if two states of polarization look very similar, right, then they are going to be near on the Poincare sphere. That's what you mean by saying that opposite points are orthogonal states. We've seen that, but that's a particular case of something more general, which we've not actually proved. If you have two states separated by gamma, they're not orthogonal, okay? So they have some overlap. What that would mean is if one of them is a feed and the other is an incoming electric field, then some fraction of the amplitude will get into that feed. And that fraction turns out to be cos of gamma by 2. Now, that's in the case of linear feeds, that's pretty clear, right? Because all the linear polarizations live on the equator of the Poincare sphere. If two of them are separated by, gamma, remember that in real space, they're actually separated by gamma by 2 because we doubled the major axis angle. And then the cos gamma by 2 is just the old law of Malus. But what's nice about the Poincare sphere is that this is true for any two elliptic things, right? Then you have transformations, right? And in the optics context, or even in radio astronomy, for example, a polarization can get transformed as it passes through a medium which has a magnetic field, right? And then if it is lossless, then it has a property that there are two orthogonal states and they are unchanged on the Poincare sphere. Their phases could change. But remember, we threw out phase, right? We throw out the overall phase. Then the transformation is just a rotation around that axis. Again, we saw the baby version of this when Fresnel told us that linear polarization entering a medium in which the two modes are opposite circulars moving with different phases, right, will get rotated, okay? So in general, any lossless transformation is a unitary transformation, which is the rotation of the Poincare sphere about some axis passing through the center. Right? So any basis change that you might want. But that's not all. Okay. I haven't even told you all the properties of the Poincare sphere, but there's a particularly interesting property. And it's particularly interesting because it was really discovered in the 1950s. Okay. So, and that is lecture 3. Okay. So meanwhile, lecture 2, we will try and get out of this fictitious world where there's only a single frequency present and talk about unpolarized light and so on. And of course, the hero of that lecture will be Stokes. Well, I think I should stop sharing.
Yeah.
And
Right.
I seem to have finished this one pretty early.
Yeah.
But
Yeah.
that leaves plenty of time for
Right, for comments, questions, discussions,
right.
anything.
Or even suggestions. If you'd like me
Yeah.
to put up something on the website, I could do that.
Mm-hmm. Yeah, I was wondering if the set of slides you used, if you would share a PDF,
Absolutely.
I can put them up, and the recordings would anyway become available. So we will
Right. I will do that. Maybe I'll convert it to a PDF and send it.
Yeah, absolutely. Yeah.
I mean,
Right.
there's no need to. Not everyone might run LibreOffice.
Yeah, LibreOffice. Correct.
So that will reach you pretty quick.
Sure. Perfect. Thank you so much, Rajaram. Yeah. Yeah, if anybody has any comments or suggestions, questions, please just raise your hand, unmute yourself, and go ahead. Yeah. It's a pretty small group. Yeah.
By the way, this is not the smallest audience that I've ever had. I
Yeah,
once
in
gave a
addition
talk.
to, yeah.
I gave a talk in France in July where everyone is at the beach. So I had 3 people. But let me tell you, they were 3 great radio astronomers. So and it was on polarization, as it turned out. Polarized maximum entropy method, which I will have nothing to say about. but I did work on it in the 90s.
You actually have more than double the audience, which as compared to the Zoom list, because we have many more on YouTube. Yeah. Yeah.
That's great.
Okay.
So I think the promise of putting lectures or recordings on the website has also encouraged some people to think that they will watch it later.
Sure. Yeah.
By the way, one of the shocks I got when I gave my first course in ICTS was that people said, "Can you record?" And they never turned up. And these are people who live there, live in the hostel and so on. So yes, can happen.
Yep.
No, and also there are people in other time zones, I would hope.
Right. Yeah, I mean, some people have a good reasons for looking for a recording. Yeah.
Okay, so that's it. I guess this was basic stuff, but I do hope that.
Yeah, I think a good warm up for what's to come, and I think moving away from the monochromatic case, we will be using all of the stuff which you developed. So I think that is great. Yeah.
That's certainly true. And Nitya had a comment, but with one comment which one could have made, and I mean, to the best of my knowledge and belief, if you follow all the conventions faithfully, you end up with a Poincare sphere with left circular on the top. Now, if you look at the sketches that I had of polarization on the Poincare sphere, they unfortunately had right circular on the top. So I hope you will allow for that. Right. But what Nitya pointed out is that some of the angles had some question marks and all that on it.
Right. I think some things got labeled as question marks. Yeah. There were 2 instances which I noticed.
Okay. Maybe I can fix that before.
Yeah. And one more thing I think which will help us next time is that your cursor was black and the background of the slides were also black. So it was hard to track the cursor.
Okay. Yeah, I can probably change. The cursor still has a white outline, but
Yeah, but I mean, it
But
was
okay, no, I can make the cursor work.
harder to
I
see.
should.
Yeah.
I
So
should,
yeah,
yeah.
sorry, I didn't want to disturb you in the middle of the talk, but yeah.
Okay, because the cursor really helps moving things
Yes,
around.
indeed, yeah. ठीक है.
I think there is a hand up. Surajit wants to
Yes.
ask a question.
Yeah, Shurajit, please go ahead. Yeah.
Yeah, so I had a question regarding the lossless transformation and the unitary matrix actually. So, so the lossless transformation is essentially the power of the field is not being changed. Is that right?
Power, the total power in the pair of fields.
Yeah. So, and the Poincare sphere is also is also a sphere of fixed radius. I think it's a unit radius. Then
yes, that's true.
so if a transformation changes, so if there is a transformation which changes the power of the incident field, it would have no effect on the radius of the Poincare sphere. So
that's
just
absolutely right. The
how
way the
is
Poincare
that?
sphere is defined,
So
you've thrown
how
away
is
the
that?
intensity and thrown away the phase.
Yes, so how is that a
Nevertheless-
lossless transformation is always unitary
but-
transformation on the Poincare sphere?
Nevertheless, lossy transformations can be represented on the Poincare sphere. Of course, if you have an equal loss and no relative phase between the two components, then the state of polarization won't change and it will remain at the same point on the Poincare sphere. But in general, one place I didn't explicitly mention this, but the Poincare sphere was forgotten for a long time and revived in the context of the optics of crystals. Okay, so there are crystals which are absorbing. So in fact, the two modes are not orthogonal, right? And the absorptions are different. And in that case, the Poincare sphere still tells you how the polarization state changes. It doesn't tell you how the total intensity changes. You're right. I may not be getting into that because not directly applicable to us at radio, but then very significant work on absorbing crystals and representing how they behave on the Poincare sphere.
So, so does that mean, so then is it right that all lossless transformations can be represented on the Poincare sphere, but all lossy transformations can't?
No, lossy transformations can be represented, but you lose information about the total intensity.
Okay, because
and the phase. And the
because
phase.
of
And the phase.
because of the complex factor which you said that they are equivalent states.
Yeah. No,
Okay.
it can be. So maybe since you have raised this point, maybe I will throw in something about lossy transformations. I'll flag that and do it at the end because it's interesting. Yeah.
Okay.
The Poincare sphere seems to be more powerful than you would think because you have thrown away so much. I should also add that in lecture 2, the interior of the Poincare sphere will start getting some meaning. Okay. So let's wait till then.
Thank you.
Okay, Rajaram, there is the comment by Prasoon who's on YouTube. I'm typing it out. So I have written almost half of it. You can take a look at it while I type the rest of it.
You're typing it out in the chat, right?
In the chat, yeah.
Yeah. Okay. In the case of interference like that of a double slit, let's say the polarization direction is along the slit. When they reach the screen, though far but at a finite distance, they reach at slightly different angles. Yes, that's absolutely right. So the kind of combination that one had in mind is not really a double slit combination because in a double slit, they are at slightly different angles, right? Which is what allows you, in fact, to move along the screen and vary the phase difference. But one can have, in fact, maybe I just want to draw a figure that you can have an arrangement in which two beams can be combined in the same direction. You need a piece of glass or something like that. And even in the case of radio waves, you can have something like a beam splitter, which is made up of wires. So really this combination, I mean, the small angle which you point out is absolutely right. So so incidentally, in radio astronomy, for example, you might have a feed, and along the axis, it may be X and Y with equal strength, but if you go away from the axis, it won't be, right? And that's precisely the angle effect that you're talking about. Okay.
Okay, yeah. Any other questions or comments? Yeah.
I see something. The direction sense of EX and EY is a little different.
Yeah, it is a continuation of the same thing. Yeah. Yeah. This is a part of the same question
No,
by.
I basically agree. So you get a small longitudinal component, in fact.
Right.
Yes. So since Prasoon raised this point, I do want to mention there is a community which takes this very seriously, and believe it or not, they are biologists. So biologists use microscopes, and their microscopes have what is called a high numerical aperture, which means the f/d ratio or something is very small. So the different rays which are being collected from the sample actually make very large angles with each other, right? And then, of course, they get imaged and so on. Now, believe it or not, biologists are interested in polarization. I learned when I went to NCBS and so on, because they put in fluorescent things and then they excite them and see. So they really have to look at a three-dimensional electric field, which lives in the focal region of their microscope. So it's just that I was sort of kind of ignoring that in this. By the way, this is equally true also of the focus of a deep dish, right? You have things coming from large angles, right, in the dish. And this takes us into things like the cross-polarization of a dish and so on. But a good point.
Okay, I don't see any other hands or anything else popping up on the YouTube chat either. Yeah.
Great.
Okay. Fine. So I think we are done for this session. So we'll meet again on Wednesday evening at the same time, 5:30 IST. Right?
Okay.
Okay. Thank you so much once again, Rajaram, and look forward to the next lecture. Take care.